Hi. This talk is about traffic engineering and Microsoft's unified network, which we call OneWAN. Microsoft's wide area network encircles the globe. It covers over 60 Azure regions and 190 edge points of presence. WANs use traffic engineering to achieve better performance than default routing. RSVP-TE is a standard protocol for doing traffic engineering inside a network, or intra-domain traffic engineering. A decade ago, cloud operators found that we could do better with software-defined controllers. We all built separate WANs dedicated for inter-data center traffic. SWAN, B4, and EBB are examples of such networks. I think I must have just knocked that. Yeah. Meanwhile, inter-domain traffic engineering is done using controllers, software controllers like ITE, Edge Fabric, and Espresso. OneWAN is the evolution of intra-domain traffic engineering that serves both internet and inter-data center traffic in a unified network. Let's look at the two WAN architecture. Regional gateways connect data centers within a region. SWAN and core are separate autonomous systems whose routers are present in these gateways. Edges only contain core routers. Inter-data center traffic flows over SWAN, and internet traffic flows over core. SWAN does SDN traffic engineering, and core does RSVP traffic engineering. SWAN optimizes with global knowledge and achieves much better performance. It time shifts discretionary traffic to achieve to decrease congestion. Not only did this improve the SLO of internet traffic flowing over core, SWAN evolved to carry critical customer workloads with high SLO. We developed Blast Shield, which allowed us to do global traffic engineering without a global blast radius. I think the bend radius is too much. We often have problems in our optical network. When the bend radius of optical fiber is too much, it creates all kinds of problems. I think that's what's happening with the cable over there. Is there anything I need to do? OK, let me switch it. Hang on one second. It's not the cable then, it's my laptop. Yeah. Right. But two WANs have some headwinds. Internet traffic is growing faster than inter-data center traffic since 2020. RSVP-TE is reaching its scale limits because of the size of core. Two WANs require additional devices and extra power in regional gateways. There can be times when one network is overutilized and the other network is underutilized, and we cannot freely use the capacities of both networks. So that is the motivation for OneWAN. But traffic engineering in a unified network is much harder than an inter-data center network. The controller has to contend with 10 times more devices and routes. RSVP-TE is very good in fast reroute, and applications depend on that. With SWAN, we had the luxury of building a new network, but OneWAN has to be an in-place conversion of SWAN and core, because otherwise the cost would be astronomical. Let's look at the design of OneWAN, starting with traffic steering, sorry. We use traffic steering so the controller does not need to deal with route scale. It uses standard BGP to resolve prefixes to controller routes, and only the aggregation routers hold full internet routing tables. OneWAN routing is in 3 parts. In this figure, aggregation routers are shown in blue, backbone routers in gray, and edge routers in black. Edge and aggregation routers exchange routes using BGP. I don't know what to do about this. I can use another laptop. One more time, I'll switch the laptop, yes. OK. Okay, where was I? Yes, edge and aggregation routers exchange routes using BGP. Every site is assigned a site label, and the controller route prepends the site label to the packet so that the next router, which is the backbone router, can forward purely based on the site label. The controller also adds a second label, which is the node segment identifier of the BGP next hop. Anytime we want traffic to fall back to protocol routes, we simply remove the site label and packet uses segment routing. The second part of the packet's journey is traffic engineering. The controller creates tunnels between sites and assigns a path label to each tunnel. It also programs all the intermediate routers. And once the packet reaches the destination site, it uses segment routing, or just protocol routes within the site. Traffic splitting is how flows are hashed to tunnels. We split traffic twice, once at the source aggregation router and again at the source backbone router. The weights are calculated based on dynamic topology, but the steering weights are computed demand obliviously, and traffic engineering weights are calculated demand aware. The reason for this difference is that there's less need for TE within a site. The backbone router also selects different tunnels based on traffic class because discretionary traffic and intent traffic is optimized with different objectives. The controller also programs backup tunnels to use in case primary tunnels go down. Next is local repair. Interactive applications like video streaming and video conferencing need fast convergence because applications can tolerate only a few seconds of packet loss. An agent running on the router can react faster to faults than a far-off controller. When a tunnel goes down, the OneWAN agent on the ingress router redistributes weights among remaining up tunnels, switches to backup or tertiary tunnels, and if all else fails, falls back to ISIS routes. In this example, A and B are primary tunnels, C and D are backup tunnels. In the all-up case, traffic is split on A and B. If A goes down, B is the sole primary. If A and B both fail, then the agent replaces the next hop with C and D tunnels. And if all tunnels fails, the agent installs a route to pop the site label so that the packet is forwarded on using the node SID. Swan measured tunnel liveness using probe packets that traveled in the forward direction on the controller routes, but returned back to tunnel ingress on ISIS routes. If a link goes down in the shortest path, both the primary and backup tunnels fail. The backup tunnel failing is a false signal. Even after the ingress router installs the pop route, packets continue to drop due to micro loops until ISIS reconverges. OneWAN uses bidirectional probes, which return back to the tunnel ingress on controller routes, which could be an existing data tunnel in the reverse direction or a probe tunnel. There is no dependence on protocol routes. In addition, we optimized hardware writes to the data plane, which was the next cause of excess delay. Local repair is now on the order of hundreds of milliseconds. This is slightly slower than RSVP fast readout, but still meets the requirements of interactive applications. Next, how we scale TE optimization to a 1,000-node network. Unlike some prior work, path computation is done online. The advantage is it can use the dynamic topology, and source sinks can be filtered based on the traffic matrix. We TE from source router to destination site, so the sink routers are aggregated by site. The net result is a 30x reduction in paths. Not only does it decrease the time and space for paths, it speeds up the optimization phase by decreasing the number of columns in the constraint matrix. K-shortest paths is often cited as the basis for path formulation maximum fairness. Even with various modifications, we find that it performs poorly in our WAN topologies because of intra-site links. Notice that path SUT is found only after 668 shorter paths in this small graph. We find that single commodity max flow pathfinders are more efficient both in time and the quality of paths returned. We use solver chaining to optimize multiple objectives. We use the solution vector of the upstream solver to construct constraints in the downstream solver. Maximum fairness does not ensure that selected paths are of least cost, and diverse path optimization uses a result of the min-cost solver to select diverse paths. For discretionary traffic, we chain the result of maximum fairness with minimized max utilization to decrease queue drops. As a side note, we integrated CLP and GLOP solvers, which give a 5x speedup over Swan's LP solver. Now, link diverse paths are not sufficient for an operational network because links share fiber spans or risk groups. In this example, path SUT only protects risk B. In the path computation phase, we use an additional finder to find risk diverse paths. Our first implementation of diverse paths was active, meaning it carried a small fraction of traffic even in non-failure cases. Now, users who care about diversity also care about latency, and they were not happy when their flows hashed to diverse paths. So we had to select diverse paths that were not too long compared to primary paths, and we could only protect 75% of traffic. Once we implemented backup tunnels, we could protect all the traffic. And backup paths are with higher amount of residual bandwidth after allocation of primary traffic are preferred so that they can decrease the transient congestion in the interval between local repair and optimization with the new topology. Good traffic engineering requires high-quality traffic matrices. We measure internet and non-discretionary traffic matrix using flow sampling, and discretionary traffic is counted at hosts. The tuple of source router, destination site, and traffic class is called a traffic trunk. Since we re-optimize every 5 minutes, the linear regression predictor needs to predict only for a short period into the future. Now, inter-data center traffic is typically unicast, but that's not the case with internet traffic. Internet destinations have different source-specific exits. We use the BGP next hop attribute in the flow record to determine the destination of a sampled flow. For example, the same destination is recorded as a trunk from A to B and C to D. Now, we built 2 generations of high bandwidth data pipelines to process IP fixed flow records and S-flow samples. Although it is a significant investment, traffic matrices from flow sampling have much higher fidelity than other techniques like network tomography. However, data quality issues do arise from time to time, and we use automatic and manual error correction. We use interface counters to correct for underprediction that arises from lost samples. Also, the linear regression predictor handles data gaps that arise when, say, an instance of a flow collector restarts. BGP load balancing can sometimes cause the sampling router to report an incorrect BGP next hop. So we use traffic matrix operations to fix up such firmware issues. Although the network is very large, the number of traffic trunks is less than order n squared. Also notice that the trunks are highly skewed. 80% of traffic trunks are less than 100 megabits, and they make up only 1.5% of total traffic. So this can be used to decrease the size of the constraint matrix in the optimization phase. Finally, traffic migration. Converting from 2 WANs to 1 WAN in a live network is like changing an aircraft engine while it's flying. We use new blast shield slices for 1 WAN controllers to isolate its faults from SWAN controllers. Slice boundaries are drawn in a way to increase local traffic, which is easier to migrate and only requires local changes. We gradually step down the RSVP bandwidth reservation to match the traffic migrated to 1 WAN. We started migration in early 2021, and 95% of our traffic is on OneWAN-TE. It has greatly improved, simplified the next generation build out of the next generation of the WAN, and decreased capacity augments by 10%. So in summary, building and operating OneWAN has been a learning experience, and I hope it provides ideas for new problems. Thank you.